What's up guys, we're going to be using SQL injection to exfiltrate the database schema from the OWASP Juice Shop web app. First of all, what exactly is a database schema? We don't really need to overcomplicate this. It's basically the structure of the database, and that includes the names of all of the tables inside the database and the various rules for what types of data can be input into those tables. What we're really interested in right now is simply the names of all of the tables in the database. Now you might think, don't we care more about the information in the tables rather than the names of the tables? And you'd be right here. The end goal is actually to access the data inside the tables. But the way that the SQL language works is that in order to extract data from a table, perhaps by means of a select query, we really need to know what that table is called first of all. I'd like to draw your attention to this search box up here, and we can test this. I fired up the DevTools window as well so we can see if there's any HTTP requests that are taking place. Let's just search for something in the Juice Shop. Let's search for orange, hit the enter key, and we get some search results here. And if you have a look at the URL, you can see that there is a query parameter there. The parameter is Q and the value is orange. If we look over on the right hand side, we see that there was a HTTP request sent to the back end. We have this search, then we have a blank Q parameter. So we can see that that parameter was not actually passed on to the back end. If we have a look at the response of that request to the back end, we see that the Node.js backend is returning a JSON object with all of the products in the shop. It's not just returning the products that we searched for in this case, it's returning them all. Now you'll see that that happens regardless of what our search term is. For example, if we directly modify this Q parameter here in the URL, and let's refresh the page, we'll see that the identical HTTP request is taking place. Q equals followed by a blank value for that parameter. In other words, it's not passing our parameter to the back end. If we search via the search box here, let's change to orange again and press enter. You can see that the query string in the URL bar changes back to orange, but there's no subsequent HTTP request that's sent to the back end. Let's try that again. Watch over on the right hand side. We're going to search for strawberry this time. So we can see that there is a request made, but it's specifically for the image, but there's no actual additional search request that's being sent to the back end. That means that this searching must be happening on the front end, i.e. via the front end JavaScript. So what's happening here is, regardless of the parameter we assign to Q, the subsequent backend request always ships with a blank value for the Q parameter there. In other words, it always returns the entire JSON object containing all of the products in the Juice Shop store. However, the front-end JavaScript does consult this Q parameter and filters this JSON object based on the search term and updates the page we're seeing with the information from the JSON object, including the subsequent call for the image. So here's the question. If that Q parameter is not even being consulted when it's sent to the back end, why is it even there? Surely the function of this request is to always return every item that's stored in the database, so why even have a query parameter here? So immediately something doesn't seem right with the way this has been configured. And what it means in our case is that this search box is probably not going to be injectable with SQL because nothing from this search box is sent to the back end. It only looks at the JavaScript object on the front end and filters through that. So if we were to enter some kind of payload such as apples with a trailing single quote and search for that, we're just going to get no results found. It's not actually querying the database because nothing was sent to the back end. However, this request, there's a chance that this request is actually having an impact on the query that's being run on the back end. So this queue is not the same as the queue you see in the browser. This particular queue is sent to the back end. So let's edit this request and send it to the back end. So we're going to try the same payload apples with a trailing single quote, but this time we know it's going to the back end rather than just querying the front end JavaScript object. Let's send that. And we get a 500 response. Here we can see a copy of the response, which is a JSON object detailing the error. And here we can see the explicit SQL query that is exposed by this JSON object. We have select all from products where name like apples with our trailing single quote, or description like apples with our trailing single quote again, and deleted at is null, order by name. Let's break down that SQL query. So select all from the products table, where clause, followed by name like. Now like might not be immediately obvious. It allows us to search for a non-specific string. We can even make our search term less specific by adding those 2% signs you see encapsulating the injected search term. And this means that there can be an unspecified number of wild characters before and after the string. In other words, if we search for A, it will give us any match with the letter A, regardless of where that appears in the string. We would get strawberry as a result, because the fourth character of the word strawberry is A. This query doesn't just return results where the name is a match, but it also returns results where the description is a match. Let's not focus too much on the latter half of the query, because we can see that our injection point is going to occur at that first search term input. So either way, we're going to have select all from products where name like, and it's at this point in the query that we can inject our SQL payload. Let's start by including some kind of arbitrary search term. Let's just put the letter A. And we're then going to immediately close this with a single quote. So anything after this part of the query is just going to be pure SQL. We're out of the string right now. We then need to close these brackets because, as you can see, there are 2 brackets. And if we don't close those, the query is not going to make any sense. This is the big advantage of being able to see the query directly. If we couldn't see the query, we wouldn't necessarily know that those 2 brackets need to be closed in order for us to have a successful SQL injection attack. But since we have access to the explicit query, we know that our next 2 characters are going to close those 2 brackets. Now, ideally, we'd like to extract additional information from the database. Ordinarily, we would do that with a select statement. Unfortunately, we don't have that luxury. We only have one SQL query and we're already halfway through it, and we've already used select to choose something from the database that we don't really want. This is where the union select query comes into play. It basically allows us to combine 2 select queries, but have all of the results displayed in a single database column. And this works for multiple columns as well. If we were selecting 10 items from the products table, we could then choose 10 other columns from a second table, maybe products version 2, and we could list them all in their corresponding rows in the query result. Now, to be perfectly honest, having worked with SQL on a daily basis for quite a number of years, I don't even recall a single instance where I've really used union select for development purposes. The main usage in my case for union select is crafting SQL injection attacks. This is just my experience. Maybe there are some SQL developers out there who insist that this is one of their absolute favorite queries available with the SQL language, but honestly, I don't think it gets used that much. Now, there's a little bit of a catch here with using union select. The number of columns from the table requested as part of this second half of the query must correlate to the number of columns requested as part of the first half of the query. So how many columns are requested here as part of the first half of the query? We have no idea. To be more accurate, we might be able to make a good guess. The JSON objects that were being received from the back end give us a pretty good idea of how many columns we're likely to expect in this particular table. But for the sake of future testing, you may legitimately have no idea how many columns there are in the table. So we're going to assume that we don't have any idea. because we don't have access to the database schema yet. That's what we're trying to establish. So job number 1, figure out how many columns there are in the products table. There's a trick we can use to establish this, but it is a little bit brute force. It's going to take some patience. We're going to say union select 1, and then we're going to end the SQL query. So our semicolon to end the query, and our comment character so that everything after our injection is completely ignored as part of the SQL query. Returning now to the original request, we can choose the option to edit and resend. Now you may prefer to do this type of work using what's known as a proxy tool such as Z-Attack Proxy or Burp Suite. But seeing as we want to focus all of our energy on SQL injection right now, we're going to use the browser's ability to edit and resend requests to the backend. So let's start constructing our SQL injection attack. So we'll have an arbitrary search term, which we'll just have as A. We're going to end the string. We're then going to close our brackets. We're then going to type plus union. Now the plus character here just indicates a space. It is possible just to leave a space here, and what's going to happen with that is the space will be URL encoded. And there's nothing wrong with that. The end result's going to be the same, but you'll find that the URL encoded string is a little bit harder to edit and resend. The plus sign doesn't actually need to be URL encoded, so it's going to be a bit easier to read going forward. You'll see an example of this because that single quote character we're sending will need to be URL encoded. Union plus select, and we're just going to choose 1. I'm going to do a plus sign, semicolon, comment characters to end our query. Let's send that to the back end and see what happens. So we get another error. Let's check out the response. So notice this, it says selects to the left and right of union do not have the same number of results columns. So what have we learnt? There's more than one column in the products table. We still don't know how many, but we know it's not 1. Probably fairly obvious that it's not 1, since otherwise the query wouldn't have said select all. But this is just a starting point to make sure we have all bases covered. Let's edit and resend. 1, comma, plus 2. And you might think, what are we selecting here? Select 1, select 2. This is just going to return the value 1 or the value 2. The whole purpose of this is to find out how many columns there are in that products table. So if we don't get an error back, it means we know how many columns there are in the products table. Same response. Selects to the left and right of union do not have the same number of results columns. Okay. Edit and resend. 1 plus 2. We'll add a comma there. Plus 3. Same problem. Selects to the left and right of union do not have the same number of results columns. You can see where the brute force aspect of this comes in. Now I'm going to save you a bit of time because I've already done this, so I actually know how many columns there are in the products table. Let's just pretend we've carried on doing this, adding 1 each time to our query, and we'll eventually find that there are 9 columns in the products table. Let's just craft out our entire query. Exactly the same format, all the way to 9, our semicolon, and then our comment characters. Let's send this to the back end and see what we get. This time we get a 200 response. In other words, no error. If we have a look at the response object, we're getting this data object back. It includes all of the headings from the product table, ID, name, description, price, deluxe price. But rather than values from the actual table, it has our union selected values 1, 2, 3, 4, 5, 6. We can even open that URL directly, and here we see the JSON response that's sent back to the browser. Returning now to our SQL injected query, which we know is going to work, it's just not very helpful at this stage. We want to try and extract actual information from the tables in the database. Now, we don't actually know the names of any of the other tables in the database, but we do know that it's an SQLite database. And an SQLite database has what's known as a schema table. In fact, most SQL databases have some place in the database where a table is stored that gives instructions on how the rest of the database is constructed in terms of which tables are available, which columns are available in those tables, what are the rules for the different data types that should be stored within those columns in the individual tables. If we head to the official SQLite page, we can see this description here of the schema table. It even tells us the name of this specific table stored in the database, SQLite_schema. It also has some alternative names, for example, SQLite_master. If we scroll down, we can actually see some of the columns that will be inside this SQLite master table. And the one we're interested in this case is this SQL column. This SQLite schema.sql column stores SQL text that describes the object. In other words, it's going to tell us how the entire database is constructed in terms of different tables. Union select is designed to be used just as the regular select query. So we can select a specific column from SQLite_master. And there we have it, our SQL payload. So we'll put this directly into the query string this time. Union select. Instead of 1, we're going to change that to SQL because that's the column we want to select. Note that we have to leave those other numbers there. Otherwise, our union query is not going to be balanced on both sides. The results here are just going to be the plain numbers, which is fine. We're then going to add plus from SQLite_master. And there we go, that's our SQL payload. Let's submit that. For every single row in that SQL column, we have a result. Of course, the titles or the keys themselves of this JSON object don't relate to the data we see, the value of that specific key. So what we have is ID of the product, but then we have the value from the SQL column for the second row in the SQL master table. And what we have here is an SQL query that creates a table. In other words, this SQLite table is storing the SQL queries that can recreate the table. So we have create table addresses. We now know that there is a table in the database with the name addresses. We also know basket items. In fact, each of these entries is the name of a different table in the database. And we can also see the different columns that are available in each of those tables. So for example, this addresses, it's going to have an ID, full name, mobile number, zip code, etc., etc. So although we don't know the values yet from these individual tables, we know their explicit design. We know the names of each of the tables. We know all of the names of the columns within those tables. And we know which types of data are allowed to be stored in those columns. So for example, ID has to be an integer. Full name has to be what's known as a varchar data type, which is a combination of numbers and letters that formulate a string. This is what's meant by the database schema. We've successfully solved that particular challenge, and we're now really only one step away from also being able to access all of the data that's stored in this database as well. We just need to reconstruct our SQL injection attack. Remember, only to use these techniques on assets that you own or assets that you've been given explicit permission to test. Anything outside of this is illegal and you could end up in jail.